Right, so we work for an organisation called the Centre for Ecology. I'm going to start by telling you a little bit about us, and then we'll start for what we're going to do for the day. We work for an organisation called the Centre for Ecology and Hydrology. That's a research organisation which is paid for by the government, but it's not a direct government department. So I think you have similar things in Japan. We have 4 sites, Edinburgh in Scotland, then in Wales, and then our headquarters in the south of England. And we're based at CEH Lancaster in the northwest. Historically, we were based in this area as a radioecology group because up here is the Sellafield reprocessing plant, which discharges very comparatively in the 1980s quite high levels of radioactivity into the marine ecosystem. So that's why the radioecology group was set up in that region. We are, however, a very, very small part of CEH. So that's all the different types of sciences CEH does. It's all types of terrestrial and freshwater environmental sciences. We don't really do marine, but freshwater and terrestrial sciences, most aspects we cover. Within there we have a section which looks at pollution and environmental risk, and I'm a group leader of one called the Environmental Contaminants group. So not only do we do radioactivity in there, we have people looking at things like nanoparticles, heavy metals. Some people do monitoring programs of things like predatory birds, see what pollutant levels are in predatory birds from across the UK. Okay, so that's CEH as a whole. In terms of radioecology, our history really starts, in terms of Kath and myself, in terms of farm animal radioecology. So 20 years ago, that's what we were doing, was largely based on looking at the transfer of radionuclides to farm animals. And why were we doing that? Well, farm animals are often one of the most important transfer routes into the human food chain. Okay, so after Chernobyl, for instance, after the Windscale Accident in 1957, if you know about that in the UK, the primarily causes of concern for human health were a high transfer of iodine through milk. In the longer term, from Chernobyl, the major contributor in Russia, Belarus, the Ukraine, has been transfer through privately farmed animal products, apart from things like mushrooms and berries, which are not farmed. And elsewhere in Europe, we've also had countermeasures in place because of the Chernobyl accident. So in the UK, for instance, we did, and in Scandinavia they did and still do. So that's why animals. Okay, so just to give you a flavour of some of the things we did. So the Chernobyl accident happened in 1986. We did lots of work around Chernobyl. Well, that led to the... Right. In 1985, people thought they knew everything there was needed to know about cesium. And then in 1986, they realised they didn't. And that also led them to the conclusion that maybe they didn't understand as much about other radionuclides as well. So the Chernobyl accident didn't only prompt us for a 20-year programme of looking at the transfer of cesium in the environment, it also prompted work to look at other important key radionuclides. So for instance there you've got the work we did on strontium. So strontium behaves very much like calcium. So we did work on potential ways you could reduce strontium transfer to milk if there was an accident involving strontium. And similarly with radioiodine, we looked at iodine and the effect of stable iodine on radioiodine transfer. One of the things we actually pioneered as well was looking at how available things are. So in 1987, the transfer from what an animal ate to its tissues was higher than in 1986. And that's because in 1986 what they were ingesting was on the outside of vegetation surfaces associated with little condensed particles, and it wasn't as available as when that was washed into the soil and then taken up by the roots. So that led to an acceptance that we needed to understand what we call bioavailability more, and we developed approaches whereby you could estimate absorption from things that were in the animal's gut into its bloodstream and transfer to milk, etc. We were responsible for, I don't know if you're aware, the United Nations International Atomic Energy Agency. Someone tomorrow is talking from that. They produce various handbooks. They do one on transfer to human food products. So we were responsible for the chapter in that on farm animal products. Okay, I'm going to skip that actually. Right, so Chernobyl happened in 1986 in the Ukraine, then part of the former Soviet Union. All right. Not only was there high levels of deposition in the former Soviet Union countries, deposition was spread all across Europe, well, all across the Northern Hemisphere really, but Europe, some countries got relatively high levels. So Scandinavia and the UK were ones where they had long-term measures in place. So in the UK, the Chernobyl accident happened on the 26th of April in the early hours of the morning. By about the first weekend in May, the contaminated air mass was over the United Kingdom, and basically deposition was related to rainfall. So when the contaminated air mass was overhead, if it rained a lot, you got more deposition. So this is the United Kingdom, and the west of the United Kingdom gets more rain than the east. And so basically you got higher levels of fallout on the west than you did on the east. That's what the ecosystems look in these areas. A lot of the areas that got higher deposition are upland areas with relatively poor soil types, primarily used for sheep farming. So between 1986 and about 2000, a lot of our life was spent, this is a live monitor on sheep, was spent live monitoring sheep and trying to understand why levels in single groups of sheep are so variable and why levels remain so high. So that became a lot of our work. So how the farming practices worked in these areas, I think someone's going to talk to you about this tomorrow, is that for most of the year, the sheep freely graze around areas that look like this. There are no fences, nothing. They just wander around in a group, and they may mix with sheep from the next farm, they may not. And then at various times of the year, for things like mating or for lambing or to have their wool removed, they're removed from areas like this, and they come down to more improved fields around farms, okay? And that was a controlling thing on cesium levels in these sheep. So if you looked at the levels over a year in the sheep, you got this up-down pattern, and the up-down pattern was as they go into the unimproved land, up, as they come onto the farmland, down, up, down, as they move between this unimproved land and the more improved farmland. Even though it's at the same altitude, it's just that those fields around the farm are on better soils with a higher cesium binding capacity, and they're fertilised with potassium and things, so they have a lower cesium uptake. Okay? Now, the management in these areas was such that it was sort of self-managing. Okay? So the male sheep are sold around about October. And because the land is that poor, they're not, on the whole, largely big enough to go directly into the human food chain. They're too small. So they actually get sold to lowland farms which have better quality grazing and lower cesium. So in actual fact, we had a self-policing countermeasure, because these relatively highly contaminated sheep were sold, they went to a less contaminated system as part of a normal farming practice, and then they lost the cesium from their body with a half-life of that. So about every 10 days you'd expect the cesium level to drop by a half. Okay? So this is a system we used in the UK. It was called mark and release. And basically, if a farmer wanted to move or sell his sheep, he applied to the local government offices for agriculture. They came along and they live monitored his sheep. Nominally, our limit was 1,000 becquerels per kilo. Because of uncertainty on this type of sodium iodide detector, in reality it was more like 700 that they passed or failed at. All right? And the farm was restricted, so sheep on these farms, they may have a few hundred to maybe 2,000. If any one sheep failed, the whole farm was under restriction. And not only that, because in these areas they mix with sheep from other farms, the sheep on all the farms around him were under restriction, okay? So in 1986, somebody stood up in the Houses of Parliament, a government minister in the UK, and said, we are placing restrictions on the movement and slaughter of sheep in areas of Cumbria, North Wales and Scotland because of a Chernobyl accident. We think they will be in place for 6 weeks. They were removed in 2012. So we had post-Chernobyl restrictions in the UK for 26 years. I'd also prompted us to do things to try and look at ways of reducing the levels of cesium in sheep. So we looked at countermeasures for them as well. There's a very effective binding agent called Prussian blue. So very, very small quantities of this agent called Prussian blue, ammonium hexacyanoferrate. If you add that to the diet of sheep, it binds to the cesium that the sheep eats and doesn't allow it to absorb it into her blood, so it excretes it in feces, yeah? That was known before Chernobyl, but the way of giving it to animals was to mix it in their feed. And that means you have to have access to the animal every day. Whereas in systems like this, and in Scandinavia, you don't see the sheep for months. Or in Scandinavia it's deer and reindeer as well. So a approaches had to be developed where you could deliver this compound to free-ranging animals. A lot of work was done in Norway, and they added it to things like salt licks, because Norway is salt deficient, so you add Prussian blue into a salt lick, and the animals come and lick for salt, and they get Prussian blue as well. That was quite effective. And they also developed things called bolus. So this is like a tablet, you can see one there. It contains Prussian blue, and you give it to the animal, and it slowly dissolves in the rumen over a period of a few weeks to months, and over that time it's reducing cesium transfer. So for the UK, what we did was see whether we could use those Norwegian ones, but in actual fact, because of how poor our systems are in these areas, the animals were too small. So with the Norwegians, we had to develop a smaller boli which we could use in our systems. This is just a little bit of modelling we did on it as well. So this is Cumbria, which is the area of England that was under restriction. And basically this is a model we ran. The only inputs to this model are cesium deposition and the organic matter of the soil. So we came up with a relationship between organic matter and plant uptake and how that changed with time. And the black line, you can see here, is actually how the restricted areas changed with time, and the red is our predictions. So you can see we didn't do bad early on. We predicted most of the areas that should have been restricted. So our last prediction here is that in 2011 there'd only be 1 square that required 1 kilometre that required restrictions. So that was quite a good prediction because restrictions were removed the year after. Say in Cumbria, so Sellafield reprocessing plants here had an accident in 1957 called the Windscale Accident. Cumbria also got relatively high levels of fallout from atomic bomb tests. So in Cumbria, we think that if it hadn't been for a 1957 accident and it hadn't been for bomb tests, restrictions could have been removed about 1995-ish. So in Cumbria, about half the cesium is from Chernobyl and half of it is from Windscale and the nuclear weapons fallout, about 50-50 from those two sources. Okay? So that's what we used to do. And we still do some of that, and at the moment we're just starting a program in Europe, but I'm leading a work package on looking at uncertainty in human food chain transfer. But since about 2012, we've had a change in the focus of what we do, and it's been more focused on developing and testing models which estimate exposure and risk to wildlife. And that's more what I'm going to talk to you about today. I think tomorrow if you come, you can get Brenda Howard here, who used to work with us, and she's going to talk about a farm animal transfer, I think. So within the environmental side, we've been looking at transfer to wildlife and also effects. Okay. So, any questions on that? Thank you. John?
So, you mentioned the cesium, how cesium is from Chernobyl and how from Windscale.
In this area, yeah.
So, how much, fallout units we are megapass kilometer in each area?
In West Cumbria, the highest we saw would have been about 60,000 becquerels per square metre of cesium-137, and that would have been split moderately evenly between Chernobyl and then the two older sources. Originally, so Fukushima, cesium-137, 134 were about a 1-to-1 ratio, yeah. For Chernobyl, it was about 1 cesium-134 for 2 cesium-137s. But the presence of cesium-134 in the original deposit is how we could calculate how much came from the earlier sources.
So what about the ratio of cesium-134 and 137 from the Windscale?
I honestly don't know, but by 1986 it didn't matter because there'd been no 134 cesium left. Because it was 1957, so it was 30 years. Yeah. But in 1957 there was very little work done on cesium, so nobody contemplated whether or not they should have restrictions on sheep. The focus of the work was on iodine-131 and transfer to milk. So in 1957 the accident happened about September, October I think, and they were disposing of milk into the early months of the next year because of high iodine levels. Okay, no more questions. Yeah, that's fine.
I really didn't understand the farming system in Cumbria.
Yeah.
So you mentioned the poor soils in the for the seed farming will be the you manufactured with the seed transfer to animals.
Yeah.
And your proposal to transfer seeds to the lowland.
Yep.
Less contaminated farms.
Yeah.
And how do you mean these less contaminated farms?
Okay, so let's see. Right, so Cumbria, the areas that had restrictions were Cumbria, North Wales, and then Scotland, and actually Northern Ireland, which is off the map. So the soils in those areas are highly organic, quite acidic, so they have a low binding capacity for cesium. Okay, so they have you have quite a high uptake into vegetation, hence why sheep are contaminated. Right, around about this time. The animals leave those farms because they wouldn't survive the winter if they were left there, and they're sold to lowland farms. So they'll be in less contaminated areas, and for two, the soils on those farms will have a higher clay content, which will mean more of the cesium is bound into the soil and less is taken up into a vegetation. So once your sheep goes from a highly contaminated farm to a less contaminated farm, it stops ingesting cesium. Cesium has a moderately rapid turnover in the body, so we actually tried it ourselves, and we removed some sheep from an upland farm and put them on a lowland farm, and they lost half of their cesium content every 10 days. Okay? So after 30 days, you've only got about 12% of what you originally had, and that's excreted onto the soil. And we also looked at the uptake then on those lowland farms of the cesium that have been excreted, but because the soils there have a high clay content, you don't then get much remobilization of what the sheep have grown there. Okay? Yep. Okay. Right. So this is how I think, wrong slide. This is how I think today is going to go. I'm now going to go through a little bit of background on environmental protection and why it changed. I'm then going to look at something which we call what I'm calling the Chernobyl question. Then Kath will give you a talk on data, and you come back to Chernobyl on some work we're currently doing in the Red Forest. And then we'll go on to an interactive assessment of the ERICA model. Interactive if you've downloaded it. If you haven't downloaded it, don't worry about it. I think we've got lunch from 12 till 1:30. I'm not quite too sure how long this is all going to take. Hopefully it'll work okay. We weren't too sure who would be here today, and we did get told that maybe some people from the public would come. So one or two bits of it might be a bit simplistic for you. So if it is, I apologise, okay? But again, any questions at any stage, just ask. And if you all think if you're all sat there thinking we understand this is too simple, then let me know and we can miss it out. Right. So this is the one that might be too simple. Right, I put when it opens up. Okay. I put this one. So it's all right. Yeah. Just slow. I put this one in because we didn't know who was going to be here and we didn't know whether we'd get members of the public. So hopefully I'm not insulting you with this, but it's just a little a refresher on radioactivity. Okay, so atoms then. Atoms are the smallest structure of a chemical element. They're composed of protons and neutrons with electrons in orbit around them. Electrons surround the nucleus, which is comprised of protons and neutrons, all right? If your ratio of protons and neutrons is unbalanced, that's when elements are radioactive. And they basically, well, they're unstable. They try to reach stability by emitting either electrons or helium nucleus, etc. through radioactive decay. They try and reach a stable status. Alright. So the radioactive decay process is spontaneous, it's random, it's not totally regular. The unstable nucleus loses energy by emitting ionizing radiation, And activity is the rate at which individual emissions of radioactivity occur. We express in units of becquerels, where 1 becquerel is 1 atom disintegration per second, or 1 atom transformation, or 1 atom disintegration per second. We also use this term called half-life, a physical half-life, so it's an exponential process. It's not quite as smooth as that. And it's the time it takes for a radionuclide. So if cesium-137, for instance, that was cesium-137, it's the time it would take for half of that to decay by physical decay, in which case it would be 30 years for cesium-137. Right. Different types of radiation. Alpha particle is the largest, basically a helium nucleus. Each particle is of a smaller and basically an electron. And then gamma, which has no charge, doesn't have a mass. It's basically electromagnetic radiation, a bit like X-rays, okay? And all 3 types of radiation can excite and ionize atoms, including in your body. Right, so we consider lots of pollutants in the environment, and in some ways you can think of radionuclides as a chemical, yeah? Cesium, americium, plutonium, they're all chemicals as well as radioactive. The difference when you're thinking about radiation is not only thinking about the transfer to organisms, but also organisms can be exposed just by being in a contaminated environment. So you have to consider both internal and external exposure, and we'll come back to this. But that's just an example from a small site we sampled within the Chernobyl zone. Well, red is the internal dose, so that's exposure from what's in an organism, and blue is the external exposure, so that's the exposure that an organism gets just from being in a contaminated environment. And that's for different organism types, so you've got things like bees, amphibians, small mammals, worms, grass, trees, okay? So in some instances, basically this shows you that the external dose rate can dominate as opposed to the internal dose rate, which is not something you'd normally be considering for other types of pollutants. So that's one difference for radioactivity, okay? Right, we think about radionuclide activity concentration in terms of becquerel per kilo. In terms of exposure, we measure it in terms of Gray, okay, and that's in effect how much energy per unit mass of a tissue, per unit mass is absorbed per unit mass of a tissue, and simply a Gray is 1 joule per kilo. You've probably heard of sieverts. Fiddle, sorry, that's a bad English word. A sievert is a Gray which is has various factors applied to it to account for the different biological effectiveness of the different types of radiation, and also some to account for different sensitivities of different organs in your body, okay? You shouldn't see sievert today when I'm talking about exposure to wildlife, because it's a unit we should only use for humans. So exposure of wildlife, we only use for Gray. Alright. Right, and just to put some of the things you'll see in a bit into context then, for wildlife doses. There have been various of these determined, but so in terms of no effect dose rates on wildlife, one of the ones that's proposed is about 10 micrograys per hour. Okay. You'll find in other publications values of, say, about below 40 micrograys per hour. You should see no effect on animal populations, not individual populations, and below 400, no effect on plant populations. I'm just showing you these now so you can put some of the numbers in you'll see in the wild context. And in the UK, for instance, background exposure to wildlife is about 0.1 to 1 micrograys per hour from natural radiation, so from potassium-40, things like uranium and thorium series, which occur in soils and rocks everywhere. That doesn't include radon exposure. So burrowing animals that live underground will get a higher exposure due to radon gas when they're underground. Okay. Right. Any questions on that? We all okay with those? So we put that in because we weren't too sure it was going to be here. Okay then. Right. Alright then, so radiation protection of the environment, which is what I'm mainly going to talk about. So over the next few minutes then, I'll give you a historical perspective of environmental radio protection, why it's changed, what's been prime motivations for that, and look at some of the international initiatives that are on the go at the minute. Right? Oh well, and aside, that is the Sellafield reprocessing plant. So the 1957 accident was actually in this building here. Right, so International Commission on Radiological Protection is one of the two organisations, I think internationally, that and the IEA, who have the biggest impact on how your national bodies regulate and consider radioactivity. Okay, so what the recommendations they make get then put into practice by regulators, by laws in various countries. Okay, so in 1977, this was the statement of the International Commission of Radiation Protection. And I'm going to read this out. I shouldn't read things out, but although the principal objective of radiation protection is to achievement and maintenance of appropriate safety conditions for activities involving human exposure, the level of safety required for protection of all human individuals is thought likely to be adequate to protect all other species, although maybe not individuals of those species. The Commission therefore believes that if man is protected, then all other organisms are protected. So in 1977 they were basically saying if you do good assessments of planned releases, existing exposure situations for humans, you don't really need to do it for the wildlife because you can assume that they'll be protected. Alright? In the 1990s, that changed a little bit to the Commission believes that standard of environmental control needed to protect man to the degree currently thought desirable will ensure that other species are not put at risk, although occasionally individual members of a non-human species may be harmed. Alright? Okay. So, at that stage, there was no requirement to assess the environment for the impact of radionuclides released. So, power stations, things like that, the Sellafield reprocessing plant in the UK, you did not have to do any environmental assessment. So, for instance, this is Sellafield, so Sellafield is A, you can start to see it in the mist, and it discharges into the sea. The coast off Sellafield is actually a marine conservation area, and then over here there are a number of protected habitats. But there was no need to assess those for the impact of radiation. And is that okay? People think that's okay? You've got lots of protected ecosystems around there, you're releasing radioactivity, but you don't have to actually evaluate whether the radioactivity is having any impact on that. Alright? Okay. Around about the year 2000, various national regulators began to require environmental radiological assessments. So this wasn't actually driven by the ICRP. Various countries, for different reasons, decided they were going to start looking at the environment in its own right and the potential impact on the environment of releasing radioactivity. So countries like the USA, the UK, originally it was only England and Wales, but now it's all of it, Sweden, Finland and Canada, all began requiring their operators to do environmental impact assessments for different activities. Okay? Right. So, why? I don't know if you noticed, but on those two ICRP statements I underlined the word belief. It's pretty difficult to actually test a belief. So the ICRP believed that, but no one actually demonstrated it. And there was no approach there where you could demonstrate it. So there was a lack of demonstration, although it was believed, no one was actually demonstrating that that was the case. It might not be valid for some environments. Some environments don't have humans. So in that picture I showed you of Sellafield, those protected ecosystems are what we call coastal sand dunes. So they're areas on the coast, nobody lives there, but they're quite important for some species of wildlife. Oceans, nobody lives in the ocean. And it's very different to how we manage the risk for most other chemicals. So all chemicals that go into production are assessed in terms of safety. And in actual fact, historically, it's probably been the other way around, that the emphasis on assessing other chemicals was more for environmental impact, perhaps, than the anthropogenic side. So it was different how we assess other chemicals. And it became a requirement for assessment under some national legislation for different reasons. I'll show you why it was the case in the UK in a while. Right, so the next one indeed. Right, so at the moment, the United Kingdom is part of the European Union. And as such, we implement European legislation in our own legislation. Okay? So there were two pieces of European legislation. One was called the Birds Directive and one was called the Habitats Directive. And these are about nature conservation. They're nothing to do with radioactivity. They're about conserving nature. Okay? And those were implemented into the UK law. And within that interpretation, it was interpreted that you needed to demonstrate that protected sites, because these are about protected sites, were not put at risk from human activities. And in the UK, we interpreted that to also mean discharges of radioactivity. Nobody else in Europe is actually interpreting it that way, but in the UK, that's how we did it. Okay? So that meant, around about 2000, the relevant government agencies had to start assessing the impact of radioactive discharges on wildlife at protected sites. And at that stage, they had no method they could do that with. There wasn't an approach you could use to do it. Okay? So they did develop an initial tool, and then in Europe and things, other approaches were developed at the same time. I'll come back to the UK example in a bit. Right. So, in actual fact, the ICRP then changed its view, and its recommendations now say there is a need to assess the environment as well as humans. Okay. And what they've done is they've now, the ICRP have come up with an approach. In ICRP tends to makes publications, and they're known by a publication number. So ICRP publication 108 sets out their framework for protecting the environment. All right. And it's to protect natural habitats, communities, ecosystems, etc. They're basing their system around something that's called a set of reference animals and plants. All right. And they've set this out so it's as close as possible to the human system of radiation protection. So in human protection, they have reference people. So in the wildlife, they have reference animals and plants. For humans, you have dose limits, constraints, reference levels, etc. And for wildlife, they've come up with something called derived consideration levels, which are micrograde per hour values for different organism types where they think you may start seeing effects. All right. Okay. And for the ICRP, then their framework is supposedly for planned, existing and emergency situations. So there are three situations that are considered in radiation protection. Planned is anything that's anything that you're planning. So it's anything that's being authorized. So it's not only a power station you may be planning to build. Anything that's already operating works within authorized discharge limits. So you call that a planned situation. Existing is an already contaminated site. So Chernobyl now, the area around Chernobyl now, is an existing contaminated site. Then emergencies is the immediate aftermath of an accident. Most of the systems for environmental protection are really aimed at planned and to a degree existing, and not really the emergency phase. All right. And the systems for assessment are relatively similar. So, human assessment, these are the types of things you consider, radionuclide source, pathway, habitats data, etc., through to a dose and an impact assessment. And what you do for wildlife is very similar. You haven't got habitats data, but you've got habits data, you've got ecological parameters, etc. And at the moment, they're not looking at radiation weighting factors and sieverts, etc. But the overall approach is relatively similar. The ICRP now has developed a number of reports on the approach they're suggesting for wildlife assessment. The general one is in 108. And I contributed to one on transfer of radionuclides to wildlife as well. All right. So their framework is based around what they're terming reference animals and plants. And there are 12 of those. And they're actually defined at the taxonomic level of family. So deer, rat, beet, earthworm for terrestrial, etc. So yeah, they're family level. So the trout is the salmonid family, etc. So what they do around these is they're collating transfer data. They come up with some shapes, some geometries, so people can do assessments, and they're collating effects data around these organism types. The other organisation, apart from the ICRP, that has a big international impact is the IEA. Their headquarters in Vienna. So their new safety standards document now states that the fundamental safety objective is to protect people and the environment. Okay. There you go. So principle 7 is protection of present and future generations. People and the environment, present and future, must be protected against radiation risks. Environment equals ecosystems and populations. And the objectives in the safety standards are prevention of radiological effects to flora and fauna, accepting man as an integral part of the environment, ensure sustainable use of natural resources now and in the future. They actually say agriculture in there as well. No one at the minute is actually sort of doing the impact of releases on agricultural animals in terms of doses to agricultural animals. Right, okay. So, there have been there have been a number now of frameworks and models over the last 17 years or so proposed for demonstrating environmental protection. Some of the common ones are the US DOE's ResRad Biota, the ERICA tool, which you'll look at later from Europe. All right, and they all tend to follow a similar sort of framework. So at the top you have your problem formulation, where you're defining the scope of your assessment, what you want to do. At this stage you'd have stakeholder input. Moving down to exposure, so looking at activity concentrations in your organisms, calculating internal and external dose exposure, total dose rate, and then impact, and looking at risk. All right. So it's a common framework that they are used in all the tools, sort of common with any other type of risk assessment, really. One of the tools that's been developed is the ERICA tool, which you'll look at later. I don't know if you have downloaded it. If you have downloaded it, then you can, if you like, play along with us. All of the approaches and most chemical assessment approaches use a tiered assessment approach, okay? Some call it levels, some call it tiers, but basically it's the same thing. So you start at tier 1, which is basically a screening risk tier, and then you move through. And what you're really doing is at tier 1, it's quite a conservative assessment approach, but it's quite simple, doesn't need many resources, therefore doesn't cost you very much. And at tier 1, what you're trying to do is remove as many sites or plants that you need assessing as possible from your assessment process. And as you go up the tiers and you need more resources, you start sampling, etc. You need more data. Okay? And the overall aim is that the level of detail needed is proportionate to the level of risk. All right. So in the UK now, everywhere that releases radioactivity is assessed. So that includes things like hospitals, and includes things like CEH, because we have a little authorization for putting radionuclides down the sink. So you wouldn't suggest that CEH spends £1 million demonstrating protection in the environment by going out and doing big monitoring programs. That wouldn't be proportionate. When you go up to something like Sellafield, then it would be proportionate to maybe have big monitoring programs. Okay. A little bit on the UK example then. So the UK started assessing effects of releases of radioactivity to the environment around about 2000. An approach for the UK had to be developed because there was no approach existing at the time. Alright? And as I've already said, in the UK, this was about how we interpret the EC legislation on protecting birds and habitats. So they had to assess all the protected sites in terms of releases of radioactivity in the UK. All right. So, all right. So that meant there was a requirement to actually develop an approach, which had to be done before any of the other European approaches had been developed. So those are all the protected sites that had to be assessed. There'll have been some out in the sea as well. It's about 430 sites. Which included 700 authorizations. So that means some sites were impacted. So an authorization is somewhere that discharges radioactivity. Okay? So that means that some sites were obviously impacted by more than one authorization because there are more authorizations than sites. Right. So, let's probably skip forward to this one. So these are the results then. All right. So at the bottom here you've got ranges in dose rate, micrograms per hour, and then number of sites at the side. Okay. So the originally it was the Environment Agency were doing these assessments. Originally they said that okay, our simplest assessment stage. So what they do is they look at the amount that's authorised for a site to release, and then we say okay, you release all of that, and we'll do some very conservative modelling and work out the level in the environment. So using a lot of conservative assumptions, assuming that everything that was authorised would be released, they compared the results of the assessments against a value of 5 micrograms per hour. All right? And if the answer was less than 5 micrograms per hour, they said that okay, this site doesn't need assessing anymore, we don't think there's a risk there. All right? So about 100 authorisations exceeded the 5 micrograms per hour, so that meant 330 didn't. So with a quite simplistic assessment, they dismissed the need to look in any more detail at 330 sites. They then start looking at more detail at the sites, maybe doing some sampling at some sites, and ultimately they had a value of 40 micrograms per hour, which if you remember from one of the slides before, is one of the recommendations below which you don't expect to see effects at population level. So they used that as their upper limit and said, your discharges cannot result in a dose rate of more than 40 micrograms per hour. Okay? And there were actually only one site that exceeded that. That was actually somewhere called Ribble and Alt Asteris, which is actually just south of Lancaster. So if anyone's ever heard of a Springfield site, it's involved in uranium processing for fuel production. Okay, and that had an estimated dose rate of 500 micrograms per hour at Lancaster. So that was it. They only had one site that would have exceeded that in their predictions. The way they resolved that was at the same stage as these assessments were being done, the amounts they were allowed to release were being assessed, and basically they just cut their permit. So they were no longer allowed to release the same amount of radioactivity, and the new allowed amount would actually give a dose rate of below 40. Alright? So at that stage the UK had probably done the assessment of most sites in other countries. Okay, again, any questions on that one? So you're going to see a lot of strange photographs of animals from Africa. We don't have African animals in the UK, it's just My laptop got wiped and all my photographs have gone, and the only ones I've got on there are from a holiday in Africa last year. How are we doing time? 10. Right.
Excuse me.
Yep.
For this example in England whales,
Yeah.
did you take the whole variety of the biological species from the environment?
They, in effect, yes. You'll see in a while. You can't try and make a prediction for every single species because there's just too many. So what most of the approaches do is have simplistic groupings of species. So there'll have been invertebrates, there'll have been phytoplankton, there'll be mammals, there'll be fish, etc. So all of the approaches tend to include different categories of organism types. So they are supposed to encompass most of the things you'll find in the environment. Yeah, we'll go a little bit more into the detail on that when we go to Erica. Okay.
So in general, should we include all species from the environment in the specific environment?
Should you include all species?
Or can we make some priority in certain types of species?
You should try and encompass all species. You're not going to go and try and do an assessment for every single species, but you should have groupings that try and encompass it. Okay. You may have situations where you're looking at protected species, and you have to assess that species by your legislation. But if you were to do a protected species, then you probably wouldn't just go and assess this protected species, because you'd also want to look at its food chain. So if you wanted to look at a marine mammal, you wouldn't just look at the marine mammal, because then you might ignore the fish or the phytoplankton, which may be more effective, but you wouldn't know that if you only looked at a marine mammal, yeah? So, no, we don't tend to focus down on specific species. Maybe as you go through the assessment levels and you get more and more involved, you might start focusing on specific species, but not right at the start, no. Yep.
So why you call England whale Natural 2000 site?
Natural 2000 it's an EC classification of protected sites. So there are sites around Europe that are called Natura 2000 sites.
Okay, so 2000 sites will be selected in
No, actually, I don't know quite where it defines from. I suspect the legislation was written in the year 2000. As simple as that. So now all those sites are called Natura 2000 sites. Right. Okay. Yep.
What is the need for decision making in this example?
Sorry?
What were the needs for the decision making for this example?
What were the needs? Within the UK legislation, the need is to demonstrate that those protected sites are not being put at risk from human activity. So that is the need. The need is, okay, so the ICRP and the IEA are suggesting things about environmental protection now, and that's driven from a radiation protection viewpoint. In the UK it was slightly different. The driving force was environmental protection and not radiation protection, and radiation protection just had to come up with an approach whereby it could demonstrate environmental protection from the conservation side of the government. Right, okay, so I'm going to move on to this. Hopefully this isn't too muddled. So this is an adaptation of a presentation myself and somebody else gave, actually the person who developed the UK approach, a guy called David Copplestone, who's now a lecturer at Stirling, at a conference last year in the Ukraine. I'm terming it Chernobyl 31 Years, the Debate. Okay. Hopefully it'll be of some interest, and hopefully I'll give it in a way you can understand. It was a long journey and we didn't arrive till yesterday, so hopefully we're awake. So a long time ago, about 31 years, in a land that no longer exists, the Soviet Union, there was a new city built, Pripyat. That says Pripyat, in 1970. Okay, this is Pripyat in the 1970s, 80s. It was a model Soviet town. It was an ideal town to go and live in. We know people who thought about going to live there because it was somewhere people wanted to go and live. It was a big modern town in the Soviet Union. Population of about 45,000 people, and it was built for one purpose. It was built to service the Chernobyl nuclear power plants. So in 1986 there were 4 operating power plants at Chernobyl using a type of reactor called RBMK. There were 2 more were well constructed, were more or less finished, and they were going to build another 2. So it would have been the biggest plant in the Soviet Union, I think, if it had been finished. Okay, so what then? Basically on the 25th, 26th of April 1986, they actually did experiments with the safety systems on the reactor. That's what it was about. It was about to look at what happened when some of the safety systems were switched off and how we would compensate for that when it went wrong. The reactor type had some problems, but it is now known, I guess it was known then as well, that when it gets to a low energy level it became unstable. Basically, the reactor got out of control and there was an explosion. Now, it wasn't a nuclear explosion, it was a steam explosion. It blew the top off the reactor. It was a number 4 unit that blew up. And that continued to burn for 10 days. And the discharges went up and down. So there was a big release on the first day, went down a bit, and then they actually increased with time before they were finally stopped. All right? So in the immediate days to weeks after the accident, something like 116,000 people and all the farm animals were evacuated from an area of about 3,500 kilometres squared. It's now bigger, it's about 4,600 kilometres squared now, because some of the surrounding areas have been added to that. Just out of interest, that's a memorial to the people who died. Right, okay. So this is what is now known as the Chernobyl Exclusion Zone. This is the Ukrainian half. So in 1986 it was all part of the Soviet Union. Now it's 2 separate countries. So up here is Belarus. That has an exclusion zone as well. It's about 4,600 kilometres squared, as I say now. So Belarus has a slightly smaller amount. It has about 2,100, and then the rest of it's in the Ukraine. All right. So Chernobyl town is actually down here. This is the cooling ponds for a reactor. The reactor is here. Pripyat town, which we looked at a while ago, is there. All right. So Pripyat was the biggest population in the area, about 45,000. Chernobyl was about 10 or 20, I think. This is the path of the original explosion, sort of they call the western trace. But because it continues to burn over 10 days and there were changes in weather patterns, you get quite heterogeneous deposition over the area. So at some stage over those 10 days, the pattern was going up to the north as well, which is what led to the higher deposition areas in Belarus and even to Russia. So there were some areas of Russia that were temporarily evacuated as well as a consequence of the Chernobyl accident. Right, so what's happening there now? I don't know if this is a phrase in Japan, but in the UK and Europe there's quite an in phrase at the minute in ecology which is called rewilding. Okay, so this is my first trip to the Ukraine. In 1993 I went and ran an experiment looking at the transfer of cesium and strontium and plutonium to cows. And we had them on a field, this field, which is about 3.5 kilometres from a nuclear plant. Okay? And we built this stable for them to use. So where I'm taking this photograph, looking this way, if I turned around, I could see directly to a nuclear power plant. All right? We then worked a little bit at Chernobyl over the next few years. We didn't work there for a while. And over the last few years, we've had funding to go and look at more wildlife studies in Chernobyl. So this was the first time we went back in 2013. I don't know if you can see this here, but this is actually the roof of this building, and we now stood behind the building looking to where I took the photograph. So in 1993, I was stood over here somewhere, okay, and now it's all forest. So all this abandoned agricultural land is turning into shrubland and forestry. It's even happening in the town. So this is Pripyat. This is Pripyat main square. Got trees and things growing in the square. The gymnasium. You've even got trees growing in the floor of a gymnasium. This is actually the sports field. So we're looking down from the stands, or where people sit around the sports centre. This is the running track, and in the middle you've got the football field and the athletics field, which is now all trees. And then obviously the iconic picture of a Ferris wheel, which was never actually used. So Chernobyl happened in late May. It was just before the big communist celebrations of May Day, and that was actually built for May Day celebrations, so it was never actually used. So actually now, Pripyat was established in 1970. It's actually been abandoned now for longer than it was ever had people living in it. And in the villages as well, so there are lots of smaller villages around the exclusion zone. They're actually sort of quite pretty, little wooden houses and things. That's what they look like now. We're all being overgrown, etc. So it's quite interesting. I don't know if you can see it. So this is inside one of the collective farm barns. I don't know if you can see here on the ground. What's actually happening is the wild horses are actually going into the barns and using them for shelter. So barns full of wild horse species nowadays. Right, so dose rates now. These are dose rates for different organism types. So you've got pine tree, grass, worms, various small mammals, then you're into various types of amphibian, and then bees at the end, all right? In microarrays per hour. These are all from a relatively small site. Oh, how far away? Maybe about 4 kilometres, 5 kilometres from a plant, no more than that. All right? And they are still relatively high, okay? So if you remember some of the numbers I've given you, I've said that 10 microgray per hour is what's used as a no-effects dose rate in some of the models. Well, all of those are above that. And 40 micrograys per hour is a value which it was previously suggested below which you shouldn't see population effects. Well, for a lot of organisms, it's above that. So undoubtedly, even now, 30 years later, dose rates in some areas of the Chernobyl exclusion zone are high enough that you would think you should be seeing effects on wild animals. All right? Without question. Okay, so accepting that, what's the debate? All right. This is it. So this is 2 screenshots from a BBC website which sort of encompasses what the debate is. I would have to say about this, we're not very good at doing presentations, so we've changed them a little bit. So your handouts may vary slightly to what you see on the screen. Okay, not much, but a little bit. So 2 screenshots from the BBC website, yeah? Just to sort of encompass things that's going on. So here we have species decline linked to DNA, so at Chernobyl. Radiation is bad for wildlife at Chernobyl. Here, same website, wildlife defies radiation. Numbers of wild animals are increasing because of no humans. Okay? So, even in the public media, you get 2 very different views about what's happening at Chernobyl. Partially driven by scientific debate, which you're going to see. Whether or not, or to a degree or not, there are radiation-induced effects at Chernobyl is probably, or undoubtedly, the biggest argument, question within radiological sciences, radiation protection sciences at the minute. And it does have implications because the public do see this. So, for instance, we know that the Environment Agency, which have a responsibility for authorising radioactive discharges in the UK, when they have public meetings, this gets brought up and they get questioned on the debate that's happening in Chernobyl. So it's not just something that's happening between scientists, it has an impact on how things are regulated in our countries, it has an impact on the credibility of our science with the public. Right. So what I'm going to do is I'm just going to look at some of the results for different types of wildlife in Chernobyl. And we'll start with mammals. So, absorbed dose rates to small mammals in the red forest. So the red forest, we'll show you some pictures of in a minute, but it's an area to the west of a reactor where the trees died in 1986. We'll show some pictures and things later. So dose rates there, we're approaching 10 gray per hour. So what's that? 1 million times higher than what I'm saying is no effects level. So they were high. Small mammal populations died. They were re-established because things moved in from other areas probably. But undoubtedly in 1986, dose rates were high enough that you would have had death of small mammals. Right, I'm going to look at the work of a couple of groups. So Chernobyl gave us a fairly unique, Chernobyl remains the largest accident to the terrestrial ecosystem. And it gave us a fairly unique opportunity to study the effects of radiation on the environment. And to a degree, that opportunity was not particularly well taken. Early on, some Soviet scientists did a little work, but not surprisingly, the focus of work early on was protection of people, etc., what to do with the power plant. So it was not a focus of work. And then early on, obviously, it was the Soviet Union was not a particularly open country where other people could go and work. From about 1990 onwards, that changed. Groups could start to go in. But that needed money, needed funding. So there was a group from the States who did quite a bit of work in the 1990s to the early 2000s. And there was another group who sort of started from the later 90s on till today. And you'll see some of their studies. Okay, so the Baker group is from the States. And they largely did small mammal work. And what I'm going to show you now is what I think is their important conclusions. Might not be what they think, but it's from reading their papers is what I think. Okay. So, at contaminated sites, they report a greater genetic diversity in 2001. But what they didn't know was that from mutations, or was that from the fact that the most contaminated sites in 1986, small mammal populations were killed, and you got movement in from the surrounding areas. So you're getting greater diversity because of immigration. And it didn't appear to give any detrimental effect anyway. Okay? Right. They also went and sampled from all over the Ukraine. So genetic diversity in bank voles in the Ukraine is very variable. But it's no bigger in the contaminated areas than it is outside. And there's no, they felt there was no data to support a Chernobyl effect on genetic diversity increases within small mammal populations. There is, you probably won't know there is, they did have a paper in Nature which said there were high levels of genetic variation. They actually had the honesty to withdraw that because they reanalyzed the data and decided that their first conclusion was wrong. Okay. Other conclusions they made: no reduced small mammal abundance diversity in the Chernobyl. CEZ is an abbreviation we use for Chernobyl Exclusion Zone. No other morphological features, no chromosomal rearrangements. And they also had a study where they brought bank voles from an uncontaminated area and put them in the red forest. Actually, later you'll actually see where they put them. A dose rate of 36 milligrams per day in that. Milligrams per day when we were doing experiments are quite high. And they didn't see any change in those. I think my comment on their study was actually only 30 days, so possibly wasn't long enough to see anything either. They, for the 20th anniversary after the Chernobyl accident, they actually published quite a nice paper sort of summarising all the things they did, called Growing Up with Chernobyl. And one of the comments they gave at the end of that was, beautiful theories are destroyed by ugly facts. So their beautiful theory of when they started in the early 1990s going to Chernobyl, that they'd see lots of radiation-induced damage in small animal populations, was destroyed by the fact that there weren't any in the work that they showed. So the conclusion of this group is basically high doses, but we're not really seeing any effects on small mammal populations. Okay? Here's a study, probably from the early 2000s, I think it was conducted. So these are the results of how, it's quite commonly used, how you can look at abundance of mammals. So basically in the winter you go out, you walk tracks, and you look for their tracks crossing it. So you're looking for footprints, and you're using that as a measure of what different types of mammals you have. So this group, Moller and Masseau, so Moller's based in France, Masseau is Masseau is an American. They surveyed all these sites. Okay, a total of 16 kilometres they walked, and looked at looked at all mammal numbers, and this is what they gave. All right. So now you have abundance of mammals against radiation, and you have what is reported to be a highly significant. I'm going to give up on this because it's not really working. A highly significant relationship between abundance and small mammal numbers. All right. So as your dose rate goes up, apparently it's not in small mammals, your mammal abundance comes down. They recorded 12 species in the study. Right then, so let's start looking at this. Well, number one, there's something wrong with it because they're actually reporting radiation in amount of sieverts per hour. So what they've actually, we shouldn't be using that for wildlife because it's only something we use for humans. What they've actually done here, and what happens in a lot of studies in Chernobyl, is they've taken out, if you work with radioisotopes, you may use a dose rate meter in the lab, you use to monitor your bench. They've gone out with one of those. And that's how they've determined dose rate. Okay? And they actually only did 2 or 3 measurements per transect. The transects may have been half a kilometre long, so just 2 or 3 measurements long there. All right? And you've seen how variable deposition is in the Chernobyl zone. Okay. Right. So, my statistics aren't great, but to my eye, if you didn't have those 3 points that it looks like there, would you really have a relationship? Or is that relationship being driven by, I would have called them outliers, but now I'm not supposed to call them outliers now. They're supposed to be called influential observation points. So, before the meeting we went to have a chat with a statistician about this, a lady called Marion Scott. She's a radioecologist as well at Glasgow University. Talking to her about the stats that were being used in studies at Chernobyl. So what she actually did was she just generated at random a data set, right? And then she put an influential data point on it and looked at the relationships. And that's what you get, all right? Bizarrely, the random data set has a significant relationship to start with. But when you add the influential data point, then your relationship gets a lot better. All right, so here we go. So a random data set actually unexpectedly had a p-value of 0.032, with quite a poor R-squared. So statistically significant, but very little variation explained. When you added that point of undue influence, then you get a really good p-value, and the R-squared value goes up to 27. Okay? But that isn't really meaningful, is it? Sticking that 1 point on, you go from that to that. Is that really a meaningful relationship? Probably not, no. And indeed, going back to this, it's significant, but only explains 7.3%. Does that really mean anything? So, significant statistical significance. Does it have any real-world significance? Well, p-value helps you. It has a role in statistics. Statistical significance. It is unlikely to observe by chance, but does it really mean anything in terms of real world importance if you're only explaining something like 7% of a variation? And a lot of the... Okay, let's just flip that one. And for instance, when you look at this one, the R-squared is not great, it's only 0.31. And a lot of the relationships you see coming out, will have R-squared values even lower than that. So they're significant, but very often they don't have a great R-squared value. So does it really mean anything? Well, or maybe, just maybe, we're going to digress here a bit, maybe nuclear power is really bad for you, especially if you swim. Or maybe uranium creates mathematicians. So I don't know if you've come across this, it's a website. I don't know how they do it, but they compile lots and lots of data and then just make, well, they don't really make relationships, they show you the problem with making relationships. So the top one there compares nuclear power generation in the US by the number of people who drowned in swimming pools. Okay? And it's quite a good correlation, isn't it? But do you really believe that nuclear power generation makes people drown in swimming pools in America? No. And the bottom one correlates number of mathematics doctorates against uranium production. Again, quite a good relationship. But probably the two are totally unrelated. I guess there's another point here. If you look hard enough for relationships, ultimately you'll find one. Right. So let's go back and have another look at this. Okay. At this higher dose rate, undoubtedly, they must be being measured in this thing we call the red forest. It's the only place that's got like contamination levels that high now. Okay, so this is an approximation of a red forest. It's, depending what you read, it's between 4 and 6 kilometers squared. All right. So this is the one thing we don't, undoubtedly no one disagrees around this one. So in 1986, the pine trees in this area died. All right. So pine trees are quite good at stripping out pollution from the atmosphere. So they got a higher dose because of that. 2, they're more radiosensitive than deciduous trees. So they're more sensitive to radiation. Some scales put them on about the same as mammals. 3, they were at a very sensitive stage of growth in terms of new growth, etc. Okay? So they got highly irradiated, and they, well, in English it goes red, in actual fact it was orange in Russian apparently, and died. So this is a photograph from the mid-90s. You can see the dead trees on the ground at this stage from the red forest, and you can see the deciduous trees are still living. This is from when we first started working in the red forest, so it's either early 16 or late 15. So now you can see regeneration of deciduous trees, a little bit of undergrowth. You can, or maybe the next one's better, that you probably can't, but you can still see the odd dead tree on the ground. It doesn't look like that anymore, and we'll come to that later as why not. You probably see it better on this one actually, can't you? So you can still see early last year, late the year before, lots of dead pine trees lying on the ground surface in that area. Alright? So there are low numbers of mammals there, it's high radiation, but it's also quite a different ecosystem. It was highly irradiated in 1986, and since then it's been going under change. And it's got quite a poor habitat status. So maybe you wouldn't expect many mammals there from that justification. It's got poor status. The other thing about it is, it might be the most contaminated, but it's actually closest to where you get most people. Because this thing up here is actually the nuclear power plant, and there are still lots of people there working on it. So until recently they were building a new sarcophagus you've seen. There were 4 reactors there, so the reactors carried on working in Chernobyl until about 2002 I think, and we switched the final ones off. So you've actually got more human disturbance in this area than you might anticipate as well. So there might be a number of reasons why you get low numbers of mammals in that area. You've got poor habitat, changing ecosystem status, and also disturbance by humans. Right. So this is similar-ish work by another group. So Jim Smith was involved in this. Right, okay. So this is in the Belarusian side of the exclusion zone, which is as contaminated as Ukraine. It doesn't contain the red forest, but otherwise it is. Okay. This is from helicopter surveys in the winter. It's easy to do in the winter because the deciduous trees don't have leaves, so you can see more. And they survey different animal types: elk, roe deer, and wild boar. Elk is moose, depending which term you use. All right. So numbers in terms of per square kilometre, and then changes with time. So with time after the accident, they're seeing an increase in numbers of those organisms. Yeah. Partially because 120,000 people no longer live there. There's no farming there. There's no use of pesticides there. So you've got these two competing things. You may have a negative impact of radiation, but you've got a big positive impact of no people. We do see a reduction in wild boar around about here. And from what we can make out from talking to people, that's probably a disease called swine fever, which caused a reduction in the numbers. Okay, so this is the same in the same paper, and now they're doing the same as in that Muller and Massot work from the Ukrainian side. They're doing observations on transects of animals' footprints in the snow to work out abundance. All right, so this is now you're in Belarus. So you've got the Chernobyl power plant sort of down here somewhere. Right, and that's what they saw on that. So they identified 15 species of mammals. Probably, if you equate this to an external dose to compare to the other work, it goes up to about 5 micrograys per hour. So over that range, they're seeing no relationship. I've only done the wolf and the elk here, but it's the same for everything they see. They're seeing no relationship with radioactivity. So if you impose that on the earlier one, that's the equivalent dose range, where if you believe the earlier one, you should be seeing an impact. Well, if you were only to look at the data in this area, perhaps you wouldn't say there was an impact in there either. Okay. What they also did in that paper. Yeah, what we also did in that paper is compared the Chernobyl exclusion zone. So in Belarus, the Chernobyl exclusion zone has been declared, if you like, a nature reserve since the mid-1990s. So a PSRER, I don't know what it stands for, but that's basically the Chernobyl exclusion zone. And the other sites on there are nature reserves in Belarus, uncontaminated areas of Belarus. So they compared animal numbers in the Chernobyl exclusion zone with animal numbers in nature reserves from Belarus. Okay? And what you see is no difference. So the Chernobyl exclusion zone has just as the same similar animal abundance numbers as do the other nature reserves. So there's no radioactivity. The only difference is actually wolves, where the Chernobyl exclusion zone actually has a higher population. Okay, so this is something that was published, I think, last year by a Belarusian American group. So they had wildlife trap cameras out, so motion-activated cameras. They use scent stations, so they actually put things out to attract animals to them. They had them at all these green dots across the area. It's a fairly short-term study, over about a month, I think. So they found no correlation with contamination density for wolf, fox, or wild boar. The only thing they did... thanks. Thank you. Yeah, good. The only thing they did see a difference for was something called a raccoon dog, which is a small carnivore, which actually went up with radiation, so you found more of those, in theory, at the more contaminated sites. Okay? So conflicting results. You've got one result saying you get a reduction, although you can query some of the statistics in there, and two of us are showing nothing. So we currently have a project called TREE, which is Transfer Exposure Effects. Every project has to have an acronym. And a large element of that is working with Chernobyl exclusion zone. I'm not going to show you much today, but we have PhD students looking at effects on bees, Daphnia, another thing I've forgotten about, fish, We're also looking at transfer of radionuclides, and we've also had a large random camera placement study. So it's actually, we weren't intending to do this at the start of the project, it's something we developed. We had some of these motion activation cameras, and we had 3 areas. A highly contaminated area here to the north of the plant, a lowly contaminated area here. So this area has contamination levels. I can find you contamination levels that high in Cumbria at home. It is quite low. And an area here was middling in contamination. I don't remember exactly now, but there were about 80 camera placements in each of those areas over a period of a year. We haven't analysed that data, so I'm not going to tell you much statistically on it. I'll just say we see lots of things everywhere. We never had a single camera that didn't have a reading, and I wouldn't intuitively say we see a difference with radiation. What I am going to do is let you have a look at some pictures. So these are actually set on, they are single shot photographs, but if you put them together it looks like things are moving. So we see lots of wolves. These ones have obviously found a little bit of bone under this snow. So this wolf is defecating. I don't know why all wolves do that. So we see lots of deer, we see these are red deer, what we call red deer in the UK. We see both red deer and roe deer. We see more red deer than roe deer probably. A lot of the animals know the camera's there. So you'll see this stag at the end is recognising the fact that the camera is there. So I don't know whether they can actually hear it because of the sounds going off. It doesn't seem to affect the behaviour of many of them. I don't know what was about this site, but no animal ever walked past the camera here. Everything ever only ran. Roe deer, so you tend to see less roe deer than red deer. Again, one who knows the camera's there. Elk or moose, depending where you come from. This one has potentially been shot. There is a little bit of poaching going on in the Chernobyl exclusion zone. Two males. We know that's an odd one. It's the only photograph. Didn't set the camera off getting there, and it didn't set the camera off going away. So these are Pavelski's horses, which I'm probably not saying right, but the only true wild horse. A national park in the mid-90s somewhere in the Ukraine had too many, so they actually put them in the zone. And they're obviously breeding. We're seeing young ones. They're obviously living a fair life, because the early ones had a brand on a mark, and we're getting photographs of some of the early ones still 20 years later. Wild boar. Wild boar have made a mess of the area, really. So all the old abandoned land is just totally churned up by having 30 years of no boar control. We also have issues when we're doing small mammal trapping. A wild boar will come in and damage the traps overnight, trying to get the cereals we put in the traps to catch small mammals. Fox, we were told we wouldn't see many red foxes, but we actually see quite a few. Badger, we see those seasonally. And then these are raccoon dogs, which we know are in the UK. Whether you have them here or not. Originally they are an Asiatic species. Hare. So hare are quite good at setting the cameras off of the night. There's no rabbits in the exclusion zone, but we do get hares. And lynx. That one's got 2 on them. The young one behind it. And you can get some quite nice photographs by putting your camera. So it takes pictures of animals with the old buildings in the background. Right. Okay, we've also got some firsts. So in November 2014, the cameras recorded a brown bear. And then we've subsequently seen that in other years. And we think we've got photographic evidence of at least 3, and people have done sightings elsewhere now. So we've actually written a paper on the bear recently. When the BBC got hold of the fact that we'd seen brown bear, they wrote a story saying it was probably the first time in 100 years. I have no idea where they got that from, but they say it was about the first time in 100 years that brown bear had been observed in this area. We're also seeing European bison. So in the Ukraine, in the exclusion zone in the mid-90s, they released the horses. In the Belarusian half, they released some bison. So this is the first evidence we have, and again they're breeding quite successfully up there now. This is the first evidence of a bison coming over a border into the Ukraine. There are not many, we've only seen 1 or 2 of those. Okay, birds. So birds are probably the group which have been most studied. So there are over 40 publications about birds in Chernobyl, and there are an increasing number about them around Fukushima now. But about more than 90% of those papers all come from one research group. And all the papers largely report negative effects. Okay, so these are some of the observed effects. Fluctuating in symmetry, cataracts, so you've seen pictures of cataracts here, so undoubtedly they're happening. Things like partial albinoism, these are barn swallows probably, tumours, and other deformations. Again, there's photographic evidence of those. And then things like some reproduction effects, deformations to sperm, have all been observed. Right, so this is quite a good one. This is actually outside the exclusion zone. This is just a study of migratory raptors in Israel, which is the type of thing you can see get published. Okay, so Israel apparently, no, but it is. It's a important passage area for migratory raptors migrating between Europe and Africa. All right, and what you've got here is changes in numbers going through the area of steppe eagle and Levant sparrowhawks. All right, and you can see it was a decrease in numbers. So this is what these people put it down to. They said because the birds were coming from areas where there'd been Chernobyl deposition, not actually anywhere near Chernobyl, but Array, so it's not in the highly contaminated areas, because those birds had been in those areas, that was reducing their numbers, reducing their survival, and reproducing their reproduction effects. Okay? But if you actually look, before 1986, there were big changes in the population of this one. So that's the reasoning they came up with, totally sort of ignoring the fact that at the same time, there are declines in many birds that do migration routes for a number of reasons. But because the Chernobyl accident had happened, they measured it, they put it down to the fact, oh, it must be Chernobyl, with no evidence. That sort of gives you an example of the type of thing that can be reported. All right, changing to another organism type then, invertebrates. In 1986, in pine forests close to a reactor, there were big reductions in the number of soil invertebrates. There were also reductions in agricultural soils. It was bigger in the pine forest because the pine forest in effect got a higher deposition because they stripped it out with the needles and the needles fell on the ground, and you get a high deposition in the agricultural. But in both ecosystem types you saw reductions in soil invertebrates. And not surprisingly that carried on until the late 1990s, but by the mid-1990s, when you were sort of seeing populations to be being restored, you may have seen some changes in species composition, but that may well have been down to a change in habitat. So we're going from farmland to different types of shrubland forest. We've got the red forest, which is an area that was killed, rather than radiation per se. Okay. So what you've got here now is a study of numbers of different types of invertebrates. So you've got bees, butterflies, dragonflies, and grasshoppers. All right. Okay. So blowing that up a bit for you, you can see it a bit more. So what you're getting is over the dose rate that you have observations at, you're getting 1 to 2 orders of magnitude reduction in the numbers of observations of those 4 invertebrate types. Okay. Right, so maybe fine. It's Chernobyl, okay? So maybe you'd expect that. But let's look at it in a bit more detail. All right? So here we have what has been calculated as a no effect level for the Erica tool. So all that reduction is happening before the no effects level we're using in our assessments. It's happening well before the values at the ICRP say there should be population risks. And it's actually happening in the range of UK natural background. Okay? So there are reductions being reported here, but they don't make sense in terms of the doses they're being reported at compared to what we know about the effect of radiation on wildlife. Okay? Now some of that is going to be an issue in terms of how dose is estimated, because it is this waving a dose meter around. That's not a total dose rate. Doesn't take into account where the animals are. It's not an internal dose rate. It's not looking at all, it's only gamma. It's not looking at all the other types of radionuclides you might get there. That doesn't explain all of the difference then. There might be other things going on there as well. So this is, I don't know when this was, I mean sometime in the 2000s. And what we're beginning to realise, and what there's now some evidence coming for, is that you go and measure something now, and you relate it to the dose rate now, and you might see something. But is that really because of the dose rate now, or is that because organisms in this area had a lot higher exposure 10 or 15 years ago, depending when your study was? And you're seeing a, if you like, historical exposure effect to organisms. And there is some evidence coming out that that sort of does exist. Okay, so one to compare that against is some work on aquatic invertebrates. So they considered lakes in Belarus and in the Ukraine. They included Lake Gleboki, which is the most contaminated freshwater body within the exclusion zone. It's here. And you can see how close it is to the plant. This is the just about make out here. This is the new containment structure they put on the plant last year. All right. And they saw no difference. So they saw no difference in the they did taxon richness, but it's a comparable measure to the numbers of invertebrates. With increasing dose rates, they saw no difference in the taxon richness of the aquatic invertebrates. And that's just external dose again for things living in sediment. So again, it's not a total dose assessment, but whatever. The most contaminated water body, maybe apart from a cooling pond, shows no difference to water bodies in relatively uncontaminated areas of Belarus. Right. Staying on that theme then, soil function. So soil function has been measured in a number of ways in the past. You can use leaf litter bags, so you put leaf litter in a net, you put it in an environment, you leave it for a period of time, and you go and weigh it, you work out mass, much mass it's reduced, you put it back, and over time you measure comparative mass loss for different types of leaves in the environment. Alright, that's one way you can do it. There are other ways you can do it now. There are these things called bait lamina sticks, which we've been using. So we're a 12 centimetre long piece of plastic, and they have holes in, and these holes are basically full of food. So you put them in the ground, invertebrates, whatever, come and eat the food, and you pull them up after a month or so, and you look at the holes in the sticks, and you can work out a comparative measure of the biological activity. And there's other microbiological ways you can do it as well. Right then, so this is been 2 published studies on leaf litter, and again we get contrasting results. So we have one here that shows a significant relationship, and we have one here that doesn't show a significant relationship. And the one that shows a significant relationship then say that because of the lower degradation rate of leaf litter, you're actually seeing a build-up of organic matter on the forest floor in the more contaminated areas, because it's not being decomposed. That's what they say in that one. We had a student who actually did look at microbial processes in soils from the exclusion zone, and she saw no effect for all of the things she looked at. In April 2016, we actually deployed bait lamina out in the exclusion zone, including the red forest. So these are the things I said they have feed that's attractive to soil invertebrates, etc. In these little holes, you put a grid of 16 out and you replicate that at a given site 3 times, and you put them up and you put them on a light table and you count the number of holes. It's pretty boring when that accidentally got 1 hole. Again, we haven't fully analysed this data, but that's what it looks like. So we're going right up to nearly 250 microsieverts per hour, and we're seeing no significant difference with increasing radiation on that. Okay, so we also need to think about how the various studies are estimating dose in the field, exposure in the field. Okay, so they're often, as I've said, using dose rate meters, sometimes reported in sieverts, at ground level or 5 centimeters. And there are sometimes relatively few of those measurements, so maybe only 2 or 3 every 100 meters along the transect. Rarely is there any consideration of internal dose, and generally, because it's doing external, now we're just looking at cesium-137 as a gamma emitter. Alright, so these are actually the same data as you've seen earlier. It's this one site where we analysed various different organism types, so bees, amphibians, small mammals, grass and trees. And that gives you a comparison of internal to external. So for most organisms actually, the external dose rate is contributing a significant component. For a lot it's over half, for some it's not, for a pine tree it certainly isn't. And in terms of internal contribution then, when you start looking at the different isotopes, so these are the main contributors to dose out there now: cesium-137, strontium-90, americium-241 and plutonium isotopes. Internally actually, the biggest contributor for all of these is actually strontium-90 now, not cesium. The actinides are not contributing very much to plutonium and americium. They appear to for a worm, but whether or not that's a real result or whether or not there's still a little bit of residual soil in the gut of a worm when it was analysed, I don't know. Alright, so dose rates are often done only looking at 2 or 3 dose meter readings per 100 metres or whatever. But deposition across the exclusion zone is very variable. It's very variable on a large scale. That means you need to start considering home ranges of organisms, yeah? It's not just waving a dose meter around. If you want to try and do a dose assessment more accurately for a given organism type, you have to potentially think about all the different contamination levels it may be exposed to in its given home range where it spends most of its time. All right? But deposition isn't only variable at a large scale or over a larger area, it's also quite variable on a smaller scale. So this is some work we did in the early 2000s. We had 3 sites, low contaminated, high and medium. They were only about 200 by 200 meters. It just gives you an idea of variation over that. So in the red you've got cesium in kilobecquerels per kilo, in the white you've got strontium. So each of those sites you've got at least an order of magnitude variation, larger in some. Okay. The next one just shows you that graphically. Okay, so that's just one of those sites. Looking at a variation across that site in terms of cesium, strontium would vary equally. So an order of magnitude in this case, 28,000 becquerels per kilo up to 210,000 becquerels per kilo. And it's actually quite a random variation. So you're into spatial modelling, but you cannot fit spatial models to it. It's at random, you can't fit a model to it. It just is quite a random variation across the sites. And you even see it on an even smaller scale. So for this sort of bait lamina work we're doing, just as a measure, when we get to our metre square, we're doing the bait lamina work, we put a dose rate meter in the middle. Then to start our work, we pick it up and move it. And just moving it 50 centimetres, you may get a dose rate change of about 3. Partially because this area had quite a lot of, so closer in to the Chernobyl plant, you get quite a bit of particulate deposition, so actual fuel fragments that came out of the reactor. So close in, it's very variable because you've got little bits of radioactivity of radioactive particles in the environment. There are ways you could do that better. So we have actually, this is one of our study animals, it's pretty bad to see, but that little mouse there has actually got a collar around its neck, and on the collar it's got a thermal luminescent dosimeter, it's got TLD. So we released those, and then over a period of about 6 weeks we recaptured them and measured the TLD so we could work out a more accurate dose rate actually on the study animals, okay? And in Chernobyl you can actually also, the group we work with, have a live monitor which can both do cesium and quite uniquely strontium concentrations in animals. Don't ask me how much strontium it works, but they can. There are other types of dosimeters you can use as well, including more complex ones which will actually give you a dose record over time. Obviously you can only use those for larger animals. So as a little aside now, I'm going to show you a video of some work one of our students is doing. So the approaches we do to estimating doses in wildlife assessments are quite simplistic. We assume a home range or whatever, and we've never really tried looking at how well we do that. So what he's doing now is he's putting various types of dosimeter on organisms, seeing how well we can predict dose rate from that. So in Norway, they got quite high levels of deposition from Chernobyl. They already had quite high levels of deposition from weapons fallout, and they have reindeer, and reindeer eat lichens, which tend to be quite highly contaminated. So they have an ongoing problem with reindeer. And Norwegian farmers are quite rich, so that means they actually have GPS collars on their animals anyway, so they know where our animals are grazing, okay? So what he's done is he's come up with an approach where he can put a box, which is this thing here, and it has actually one of each of these dosimeter types in, so we can compare it. And then they're being re-released, so we know where they are from a GPC, and we're getting the dose rates as well, okay? So, if this works, you can have a look what he's doing. He has now got his results. I can't talk about those because they are quite fresh. It may amuse you to see what he's been doing. So before I start this then, so this student is from Thailand, okay? He thinks 30 degrees C is quite cold. And we sent him to Norway in winter. Is this going to work? Sorry, it worked for me before. I could move it between the screens. Thank you. I'm trying to duplicate, I think.
Just waiting for the connection. I think it's I can see that image. I'm not sure about that.
Sorry, I did test it before we started and it worked. Extend it and see if that works.
Is it the simple slice or the video?
No, it's a video of
videos?
No, there you go. Okay, hopefully it's worth the wait. Cool. Yeah, okay then. So he's from Thailand. You think some 30 degrees C cold? That is not the right thing, is it?
I guess so. Shall we try another monitor? Or?
You could. Let's do it one more go.
Sure.
Imagine you got a job in Norway, of course. Pays well. It won't run on this one. Maybe it's going to Oh, good. No, we haven't got sound, don't worry about it. Take to try out if you want, yeah. So this is so the Norway, the reindeer are gathered, so they can slaughter some of them basically. So this is them now being gathered, driven into an enclosure. I've never seen a reindeer, they're not very big actually. Both males and females have horns, and basically they stand with some cloth and herd them in. Now this is actually Move, the student. Using dogs as well. Going in the enclosure. You might see one or two of them having GPS collars on us. Oh, there you go, that's got one. It's just running past. Okay, so the real purpose of bringing them in is to screen them for which ones they slaughter and put into the food chain. But while they were in, fitted these boxes to the collars which have the GPS receivers on them, and they went back a year later and took them off. So this is the Norwegians live monitoring the sodium iodide to work out the concentration of cesium in cesium 137 in the muscle. It's a 3-inch sodium iodide, sorry, we still talk about sodium iodides in inches. So this is Moo connecting the box with the dosimeters into the collar. That is the GPS receiver on the collar. A little waterproof box. What's going on there now? So it has 4 dosimeter types in. There's obviously quite a bit of thought in the box because it couldn't affect the balance of the collar, and obviously it couldn't interfere with the sharp bits that dug into a reindeer's neck, etc. At the same time, they're changing the batteries on the GPS unit. You can, if you want, go online and you can see all of these reindeer. There's a site you can log on, and all the reindeer have a name. It's not his, it's a commercial site to do the reindeer tracking in Norway. See where they've been for a week. And once that's on, they're released, and they were actually gathered again, brought together again next September, just check they were okay. And then in the following December they were regathered and the dosimeters were taken off. Obviously he's making sure it's going. Okay? So I can't show any results from that yet, but I thought you might like to see a picture of reindeer in Norway. So there are ways basically you can do your dose assessment better. Stop that. I'm waving a dosimeter around. Okay, so that's the situation in Chernobyl. We are now starting to see also some conflicting results coming out of studies on wildlife around Fukushima. This is just one example I'll show you. So this is one of the blue butterfly studies. So it's reported the larvae of a butterfly were fed plants harvested from the evacuated area. And that reported an LD50 of 1.9 becquerels. Okay. They didn't do that as a dose rate. We actually worked it into a dose rate, and we did this in a way that gave it the highest. There wasn't much information in the paper, but we did it in the way that gave it the highest dose rate that was possible. And so the dose rate came out for an LD50, so half of them died apparently, at 8 grays per hour. So below the no effect dose rate, getting into the higher end of natural background. And from previous studies for this type of species, we'd actually anticipate an LD50 or something like a grey. So we are starting to see sort of same issues of potentially how people are interpreting their results, and does it all make sense? Alright. So a quick summary on Chernobyl then. There are, as you would expect, there are dose rates of air still to be given effect high enough to give effects now. We're seeing effects ourselves, so in the studies our students are doing with bees and things, they are seeing radiation effects, and to be honest, potentially at lower levels than we thought. Alright? But there are many studies reporting, I put significant, because whether or not they're significant or not is a bit debatable when you look, effects at really what are quite unbelievable dose rates. Natural background radiation dose rates, in 2 orders of magnitude reduction in abundance. Doesn't really seem that probable. Okay, so some of the reasons behind that of the dosimetry is incomplete. However, if you made that dosimetry complete, at a guess, it wouldn't increase the dose rate by more than a factor of 10, which would help resolve some of the issues, but it wouldn't solve it all. Because interpretation, what's significant versus what's meaningful, there are lots of confounding factors like the poor habitat. The highest contaminated sites are this changing habitat, which was actually killed in 1986, has been recovering in a different way. Also has quite a lot of high human interference. Do you have this sort of historical dose effect, but what you're actually seeing now isn't because of the dose now, you're seeing something because of the dose 15 or 20 years ago when it was much higher. Some studies don't have a control. So some studies will say, there's one last year, there's a high level of cataracts in the eyes of small mammals in Chernobyl. They did not have a control in that study outside the zone. So you don't know what the levels are outside the zone based on that. But part of the issue is it's quite easy to get something published that says we see an effect on radiation on wildlife. It's a lot more difficult to get something published in a high-profile journal that says we don't see an effect. Consideration, exposure, history, site history, I've already considered. Okay. So, as I said at the start, this issue is probably one of the biggest questions in radiation protection that we're dealing with in Europe. And it's not just theoretical, it does have an impact on how the public view the science we do, has an impact on the regulators when they're trying to regulate releases, that if specifically this is the question the UK regulator got, so they're saying, well, 10 micrograms per hour, below that we don't need to assess, we think it's safe, there's going to be no effect, don't worry about it. And then you'll get somebody from the audience who will stand up and say, but hang on, from Chernobyl there are people who are seeing effects at 0.1 micrograms per hour, and you're ignoring them. Okay, any questions on that? Now, before I said the red forest doesn't look like that anymore, it now looks like that. I'm not going to tell you about that now, I'll tell you about that later. Okay, any questions? Go on, it's fine. Yeah?
So from these presentations, we only saw the results of the animal, intensive animals in the high contaminated area, and how is the effect of the plant vegetation in the affected area, effect of the vegetation on the animals. Because we can simply think the plant species might have decreased after the access to the high radiation, and that would affect the
Right. I think undoubtedly there is an element of that there, which is why when considering places like the red forest where the trees die, we're saying you need to think about site history. So that area now, it was coniferous forest, those trees died, it's been recovering. The habitat quality in that area is quite low. So because of that, perhaps you wouldn't expect very many mammals there, because it's not got a habitat type which can support very many mammals. Yet there is an element of that happening, yeah, in the more contaminated areas at least. And then all over the zone, you have this effect that it is changing. So what was agricultural land is becoming scrubland and forest, and all that is merging into a combined effect. You have different things going on. So yeah, undoubtedly you have a negative effect of radiation in some areas, but you've got changing habitats, and then you've got this big thing of you don't have any people in most of the area now, and you're not applying fertilizers or pesticides. So you're seeing an increase in some populations because of the removal of man.
So we saw the correlation between the number of mammals and the radiation, the dose rate, the picture. So we can clarify the different mechanisms, different effects of the
Whether or not you can clarify between the effect of man and the effect of radiation, no, is the honest answer to that. From the studies that have been done to date, you couldn't do that. No. Okay. Yeah. Any others? Nope. Look it out. Right. So, last year we actually ran a workshop in a town quite close to Chernobyl, based on thinking about this issue, where we had people who were involved in effects studies, both laboratory and in the field, people who do chemical effects studies, scientists from Ukraine and Belarus. We actually also had people from Emitter and things there. Anyway, one of the conclusions that came out of that workshop was that a lot of the argument would be solved if, when people published their studies, they published the data along with it. So, I mean, I've stood here and I've come up with various reasons why maybe I don't believe that mammal study. If the data was there, we could say, okay, you're quite right, you're right, it's right what you're saying. Or we could say, hang on, looking at the data, this is a different interpretation. Well, that's not happening. And it's something that should really be encouraged, that studies on effects in Chernobyl, well, should be encouraged anyway for anything, studies on effects of wildlife in Chernobyl and increasingly of Fukushima, if people publish the data sets behind that, then we won't be having as many as these arguments, because we can look at the data in different ways and either agree or come up with alternative conclusions.